Hello friends, welcome to another video on my YouTube channel on neural network. So as you know, in my previous video I have explained about the neurons and the neural networks, about the biases, inputs, activation functions and the weights. So if you have not watched that video, please go through that video first and then come back to this video. In this video I will cover the backpropagation and how neural networks actually learn how the weights and biases change according to the outputs of the neural network and how do we train them. So let's start with this video. So for training a neural network, let's assume we have a data set like this, in which we have name, weights and height of that person, and based on the height and weight we are just predicting the gender of that person. So as you can see here, if you look for common features in this data, so if the height and weight are more, it is generally male, and otherwise it's female. So we will train our neural network on the same data. So let's create a simple neural network with the weights and heights as an input to it, and one hidden layer between it with two neurons, and then a final output layer with one neuron. We have only one neuron in the output layer because our prediction is simple, which is just a male or female category prediction, and just one neuron is fine for that. So as I have already explained in my previous video about weights and biases, in this video we will just talk about how to process the data and how to pass the data into the hidden layer of neurons to train our neural network. So before passing this raw input to our neural network, we just process it a little bit. So we represent the male with a 0 and the female with a 1, and we also shift the data to make it easier to use. So here what I have done, I have just subtracted the weight by 135 and height by 66. So all these inputs I have just subtracted them by 135 and 66 and written the result here. This we have done to neutralize the data because all the numbers are here are positive, right? So to neutralize the data, so some values will be below 0, some will be above 0. So for that purpose we have just done this shift. So normally while doing the shifting we use the mean of the weights. For example, you'll sum out all these weights, we take the mean out of them and we subtract these weights by that mean. But here randomly I have just taken 135 and 66 at the as the shifting number. So that's what I have written here. We often shift the center by data by subtracting the mean. Sometimes we also scale by standard deviation, and this is called normalization or standardization while training the neural network. Now why it is needed? Because centering around 0 helps optimization, because here if you will see, the data is not centered around 0. All the weights are positive and are greater than 0 by a lot. But here if you see, the inputs are centered around 0. So if you will see, this is the maximum weight we have here is 25 and the minimum we have here is minus 15. So although the data has been changed, but as it has shifted by a fixed amount, fixed bias, so it doesn't matter, and it has also centered around the 0. That helps in optimization of the neural network and calculating the loss and everything. So if features have a large positive mean, neurons start with biased activations. That is why we shift them downwards around the center. Shifting by mean means input 0 centered, so gradients are more balanced with positive and negative inputs. This prevents the network from drifting in one direction during training. So let's take an example. Let's say if all the inputs are positive, say 10, 12, 14, and you use 10h, which returns the output within the range of minus 1 to 1, the neuron only sees the positive side of 10h. Because applying 10h in all these values will give you a value between 0 to 1, right? You will never get a value between minus 1 to 0. So neurons will become biased. They will always go to a value from 0 to 1. That is why we center them around between from 0, so that the range and the activation function works properly and the neurons see both the sides of the data, negative as well as positive, and that makes the learning easier for them. It also avoids unnecessary bias shifting. Centering them also avoids unnecessary bias shifting. the bias term in the neuron has to work extra if the inputs are not centered. For example, when the inputs are not centered, the weighted sum, which is WIXI, which we have already seen when I was explaining weights and bias. Let's go back a little bit. So here if you see, the output of a neuron is the dot product of weights and the inputs plus bias, right? We have already seen this. Then this weighted sum is passed through an activation function, and that becomes the final output of the neuron, right? So if the data is not centered around 0 and let's say mostly positive, then the weighted sum is also large, right? Because all the data is positive, usually our weights are also positive, so the total sum will be large, right? So to make the neuron output a useful range between 0 for 10H, the bias has to cancel out this large sum. So bias is used to shift the graph up to some point, right? As I have explained earlier. So as our weights are large, right? So graph will be already shifted to one direction, right? So bias, for bias to cancel it, the bias has to be large, right? So the pressure on the bias will be more, right? So to reduce that burden on bias, we compensate the data so that it could be centered, and it will be easy to train them and shift the bias and weights easily. It also improves gradient descent stability. If the data is not centered, weights update may be zigzag heavily. So centered data it leads to smoother gradient paths and then faster convergence. This means while updating the weights are not decreasing and then increasing, then decreasing, then increasing, things like that. They will just follow a uniform path, and it will lead to faster convergence, which means it will lead to it will reduce loss faster, and neurons will learn faster as well. So this is what it means. Smooth gradients pass, it means fewer oscillations, like fewer loops needed, and network reach the optimum faster. It works well with the activation functions as well. For example, sigmoid, tanh, they are zero centered data and they prevent saturation. So ReLU, it also helps keep some activations positive and some zero, avoiding dead neurons. If the input data is not centered and mostly positive, many neurons receive positive input, so ReLU outputs positive values only. But some may become too large, which leads to exploding of activation functions. Because as in our case, as we are taking weights and heights, right, it will be mostly a positive number. So there could be data sets where the numbers are too large, weights and heights are like in 3 digits, right? But there could be a data set where the positive numbers are very big. That could lead to exploding activation functions, because they will stuck at the positive side only, right? So to avoid this kind of thing, we centered them. If the input data is not centered and mostly negative, many neurons output 0. These neurons are effectively dead. So in this case, in the ReLU function, if the data is mostly negative, because ReLU keeps the activation functions between positive and some 0, right? So if the data is mostly negative, many neurons will output 0, right? And once they output 0, this 0 will be passed as the input to the next layer, right? And there the weighted sum will become 0. Whatever gets multiplied with 0 will be 0, right? So they are always stuck to the 0. Hence the neurons will effectively dead. They will do nothing in the learning. So centering data around 0, some inputs are positive, neuron activates. Some inputs are negative, neuron output 0. This creates a healthy mix, like some are them positive, some are negative. This creates a mix of the neurons, like all the neurons do not explode or all the neurons do not become dead. That creates a mix of them, and that helps in preventing neurons from dying or saturating. That these are all the reasons why we center the data around 0 before passing it to a neural network and train it. So let's see what loss is. Before we train our network, we first need to find a way to quantify how good it is doing, right? So let's say we had this data, the same data, and we have some predictions. So our true prediction is, like, the truth is Alice is a female, Bob is a male, Charlie is a male, Diana is a female. So these are our true values, right? But our predictions are, let's say, like this. All of them are 0. So half of them are true only, right? Half of them are false. So our neural network is not doing so good, like it's only half true. So how do we find out how our neural network is doing, like what is the loss? That means how much it is predicting correct. So that we usually do by finding the mean squared error. In this case, we just subtract the actual value, which is y true, by the predicted value, which is y pred, squaring it and taking the mean out of it. In this case, whatever the result will be here, it will be our mean squared error and the loss of our neural network. And based on the loss, we update our weights and biases to make the neural network learn and perform better in the future. We will see how this works in the later in this video. So let's break this down to n, which is the number of samples, which in our case is 4. Y represents the variable being predicted, which is the gender. Y true is the actual value of the person, of the actual gender of the person, represented by 1 or 0. Y prediction is the predicted value given by our neural network. And as we know, y true minus y pred square is the squared error, and when we take a mean out of it, it is called mean squared error. So let's keep in mind all these terminologies. We will be making use of them to find out how we update our weights and biases while training the neural network. So better predictions is equal to lower loss. So if all the predictions are correct, right, the loss will be 0, right? So training of neural network means minimizing the loss as much as possible. As the loss will minimize, our neural network will perform better, right? So we now have a clear goal, which is to minimize our loss. So for simplicity of all these calculations that we are making, I'm just taking only one input as a in the calculations. So let's say we have only one person, which is Alice, and these are the weights, heights, and gender for that. As we know, our MSE is this, the mean of y true minus y pred square. Since our data set only contains one person, we can just directly put the values, right? So while putting the values, we know y true is 1, y prediction is something that will come out of a neural network, and as the total number of data set is 1 only, the MSE will become 1 minus y pred to the whole square. So our neural network looks something like this. We have two neurons in our hidden layer and one in the output layer for simplicity and to simplify our calculations. These are the weights that are passed to the hidden layer. Weight and height that belongs to the dataset. These are the inputs, and these are the weights for the first hidden layer. W1, W2 are the weights for neuron 1. W3 and W4 are the weights of neuron 2, and W5, W6 has the weights of output neuron. Similarly, each neuron has their own bias as B1, B2 and B3. Then we can write our loss as a multivariable function, right? Because our loss depends on all these inputs. So first, weight, height are passed to the hidden layer along with the weights and biases. Then the output is passed to the output layer along with these weights and the bias. And then whatever output we get, we pass it to this function and we get our error. So our error is indirectly depending on all of these inputs as well, right? So our loss is actually the multivariable function of all these weights and biases, right? And we have to update them accordingly based on our error. So to find out how our loss will be changing when we change one of these input, for example, let's say W1 or W2 or B1, to find out that, we take help of partial derivatives. So to understand it, you will just need some basic understanding of partial derivative. If you can, it will be helpful if you just look into it for some time and then come back to this video, but I'll try to explain it as much as I can. So our loss is this is our formula for loss, right? Now to find out how our loss will change if we change our W1. This means if we increase our W1, whether our loss will increase or loss will decrease, or if we decrease our W1, whether our loss will increase or loss will decrease. To find that out, we just take a partial derivative of dl by dw for this function. as our loss is not directly depending on W1, right? Our loss calculation directly depending on ypred, right? Ypred is another variable and it is the output of our neuron, right? So we use the chain rule, which is the chain rule of partial derivatives only. So dl by dw1 will be dl by dypred, which means our loss is depending on ypred and ypred is depending on w1. So dl by dypred into dypred divided by dw1. So this is the chain rule. Because our loss is not directly depending on W1, right? It's depending on ypred. Then ypred, if you will look into the formula of y prediction, it's like W5 into W6 into the outputs of these two plus bias, then activation function, right? And again, W1 is ypred is also not directly depending on W1, right? It again depends on H1, then again depends on W1, right? H1 is directly depending on W1. So first we will calculate del by dypred, then we will calculate delta ypred by delta w. Let's call it delta. So we know our ypred function is 1 minus ypred by whole square for one data set. For all these calculations, just assume we have only one data. Now if you will use the a minus b whole square, we know the formula is something like this: 1 minus 2 ypred plus ypred whole square. This is our function that we have. Now if we calculate dl by dypred, it will be like taking partial derivatives of all these three terms independently, right? In the derivations, you just if they are like simple plus minus, you just take the derivatives of each term independently, right? So as one is constant, it's simply 0. dl by dypred of 2 ypred is 2 minus 2 because it's negative term. Similarly, dl by delta L by delta ypred of ypred square is 2 ypred. It's just the basic derivations. So we got our dl by dypred. Here f is our loss. Delta L by delta ypred is minus 2 plus 2 ypred, which is the same thing. We are just putting this value here. So delta L by delta ypred is equal to delta of 1 minus ypred ka whole square divided by delta ypred, which turns out to be, we take the minus 2 as common, minus 2 into 1 minus ypred. So this is the value of our first term, which is delta L by delta ypred. We still have to calculate our delta ypred divided by delta w1. Because ypred is directly depending on w1, we again divide it. So as we know, our ypred is our output function, right, which is w5 h1 plus w6 h2 plus b3, where h1 and h2 are the outputs of these two hidden neurons, right? Here we divided our, again I'm repeating it, so delta L by delta w1, we divided it into two terms, right, because loss is depending on ypred directly, right? So delta L by delta ypred into delta ypred by delta w1. But again, ypred is not directly depending on w1, right? Because if you will see this formula, there is no w1 here. Here we have w5 h1, w6 h2 and v3, right? So again we divide this second term into two terms. Delta ypred by delta w1 equal to delta ypred divided by delta h1 into delta h1 into delta w1. Here h2 is depending on w3 and w4, right? h1 is the only term which is depending on w1 directly, right? So we used h1 here. We tried to find out when we divide this term into two terms, we will use h1 as our partial derivative, because the loop is like that, right? Loss is depending on y prediction is depending on h1 is depending on y1, right? So if we do h2, then we will not be able to calculate this ypred divided by delta w1. We will be able to calculate delta ypred by delta w3 or w4, but to calculate w1, since the loop is like this, right? Output is depending on h1 and h1 is depending on w1. We calculate delta h1, and then we apply the chain rule, which says delta ypred by delta w1 equal to delta ypred by delta h1 into delta h1 by delta w1. So we know our ypred is let's quote it as z, which is w5 h1 plus w6 h2 plus b3. So it's easy to calculate this term, right? Because y period is directly depending on h1. So y period is, let's say, function z. Then we calculate h1, which is function z into delta z by delta h1. So here, as you remember in the neuron, this is just the weighted sum. It's not the h1. h1 is calculated by passing this weighted sum into an activation function, right? So that is what we have written here. So we assume that this weighted sum is represented by z, then f is our activation function, and that's how the y period is fz. So if we calculate delta y period by delta h1, according to the chain rule, it is f dash z, which is the derivative of this function, into delta z of delta h1. As delta z of delta h1 is easy to calculate, right? So although these w6 and h2 are variables, right? But when we calculate a partial derivative based on an input, we just consider that input as variable, and we assume all the other inputs are constant. So here we'll just assume w6, h2 and b3 are constant. So when we calculate delta z by delta h1, we just treat them as a constant and they will just move out of the value. So here h1 is the only variable, so that is why delta z by delta h1 is only w5. So delta y period by delta h1 is derivative of this activation function into w5. I hope you understand it. I'll just repeat it again. So first we initially divided our loss into two terms because our reduction is depending on h1, h1 is depending on w1, and so that is why we divided into two terms. We first calculated delta L by delta y period, which we have here. Then as our y prediction is not directly depending on w1, it's depending on h1, and h1 is depending on w1, we again divided it into two terms, which is written here. Now delta y period is a weighted activation function where the weighted sum is passed, right? So when we calculate the derivative of this, which is delta y period by delta h1, this is derivative of that activation function into derivative of z, which is delta z by delta h1, which turns out to be w5, and that is what we have written here. Similarly, as we have this h1 as so here the same thing, right? For h1, this we did for output, the O1, if you remember from my previous video, O1. Here h1 again is this thing, right? This f is an activation function. Here we are passing the weighted sum of w1 x1, w2 x2 plus b1, just like we did here, where z is the weighted sum. We pass it to the activation function and our y period is calculated, right? Similarly, h1 is the weighted sum of this passed into an activation function. So by the same formula that we did here, we know delta h1 by delta w1 is x1 into derivative of this activation function with this input. So now we have our delta h1 by delta w1. This we have calculated. And we also have calculated our delta y period by delta h1. This is our first term, this is our second term, and by multiplying these both terms we get our delta y period by delta w1, which we pass here in the first calculation, and we also have our delta L by delta y period. So now we have values for all our derivative terms. The only missing part is how do we calculate this derivative of this activation function. Now for our activation function in this neural network, we are using sigmoid, which is this. So let's assume all this input, this weighted sum is, let's represent it by x. So our activation function is looking like this. Now if you will take the derivation of this activation function based on x, it will be looking something like this, fx into 1 minus fx. So I have just copy pasted the derivation of a simple sigmoid function, which turns out to be fx into 1 minus fx. We will use this terminology directly here. So our delta h1 into delta w1 will become x1 into this terminology, and this derivation will become w5 into this terminology, which where x will be w1 x1 and plus w2 x2 plus b1 in case of h1, and w5 h1 plus w6 h2 plus b3 in case of y-plat. I hope this is all clear. If not, please go through the video again, and I think it will be helpful if you know a little bit of mathematical calculation, how this backpropagation is calculated. This will help you in actually understanding how the neural networks are trained and how the weights are updated and make the neural networks learn about the data. So now we have all our calculations ready. Now we want to calculate the partial derivative. So let's say we again take the same input, single input for Alice. Now we are going to pretend that Alice is our data set. Now we'll just put all our values into it. So we'll just take all our weights as 1 and all our biases as 0. So just to make the calculations easy, I'm just taking all the weights w1, w3, 4, 5, all the weights as 1 and all the biases, which is b1, b2, b3 as 0, and we're just passing this input here. So if I will pass -2 and -1 as the input and weights as 1 and biases as 0, you will see something like this, right? -2, -1, 0. F is our activation function, which is sigmoid. So activation function sigmoid of -2 plus -1 is this 0.0474. Similarly, our w3 x1 plus w4 x2 plus b2, this is our other h2, it turns out to be 0.524 by passing this input and weights. Now we have delta L by, we already know delta L by delta w1 is delta L by delta y-prat into delta y-prat into delta h1 into delta h1 weight into delta w1. We have the values, we have the functions of all these three, right? We know delta L by delta y-prat is minus 2 into 1 minus y-prat, which we calculated just here. Here it is, right? So we are just passing values to all these functions that we have derived. We are just keeping them in place and we're passing the values that we have here. So we know delta L by del y-prat is something like this. We pass the values and it turns out to be minus 0.952. We know delta y-prat by delta h1 is w5 into activation derivative of active function of this. So we just did this. W5 is 1. We have this term ready, which is 0.074 plus 0.0474 plus 0, and the activation function, this is passed to the activation function, the same sigmoid function, derivative of sigmoid function, and we know the derivative of sigmoid function is this, as we have calculated earlier, right? Fx into 1 minus fx. So we are doing the same here, fx into 1 minus fx, which turns out to be 0.294. Now we know delta h1 by delta w1 with the same formula is this, which turns out to be minus 0.094. When we multiply all three of them, we get 0.0214. So here our loss, not the loss, the term is positive, right? This how the loss, when we try to find the partial derivative of based on w1, the term is positive, right? So this tells us if we increase our w1, let's say if our weight is 1, if we make w1 as 2, then our loss will also increase by a little bit, because the term is very less, right? So we can say if we increase by 2, then our loss will surely increase by a little bit. Even if by little, it will increase. The main significance is on increase of w1, the loss will increase. So to minimize the loss, we need to decrease our w1. We are using 1 as weights, right? We will just use 0.8 or 0.6, something like that. But to minimize our loss, we need to decrease our weight 1. That is how we calculate how our loss will increase or decrease on increase or decrease of a weight or bias, and based on the result, we either increase or decrease our weights and biases. So there could be 4 scenarios. If the delta L by delta w1 is positive, which means w1 will decrease. If we decrease that weight, then the loss will decrease. If the delta L by w1 is negative, that means if we increase our weights, then our losses will decrease, because the term is negative, right? The situation will be reversed. In case of positive, increasing in weight will increase in loss, decreasing in weight will decrease in loss. But if the term is negative, the situation is reversed, right? If we increase our weight, then the loss decreases. If we decrease our weight, then the loss increases, right? So to update our weight, we just use a simple formula. We just subtract whatever is our output of this derivation is from our weights. Here this n is our learning factor, which could be a really small value. So it's just a constant value we can keep, and we just subtract this by our weight. So if the term is positive, which means decreasing the weight will decrease our loss, right? So this whole term will be positive and the weights will reduce. At the end, the weight will be reduced. If this term is negative, then we know to decrease our loss, we need to increase our weight, right? So this minus minus will cancel it out and the W1 will increase and hence decrease our loss. That is how we updates our weights and biases for by passing all the inputs step by step until our loss is minimized as we want, and that is how we train our neural network. Let's see all this in practice. I'll just move up a little bit so that I can just compare it with the code. Let's move to the code. Okay, let me start by the beginning. So as in my previous video, I have already shown you this neuron thing, right? How the neurons are calculated and how the neural network is formed. I have already demoed it in my previous video. You can just go back to it and watch it out. So I'll jump directly into the training part. Now in this neural network class, let's go down. So this is our data set. We have just kept the same data set. I have just shown you with all the 4 inputs: Alice, Bob, Charlie and Diana. This is not the one. Let me go up. Yeah, this is the one, right? So the same data set, I have just mentioned it in the array format. Then we know all the true values for this training data set, right, which is 1001. Then we create our class and we just pass this data as well as true values to our train function here. Now if we go to a train function, let's see how the neural network is initialized. Now I'm just assigning some random value to my weights and biases, and then after that in the feed forward I'm just using the sigmoid as an activation function, and I'm just passing the weighted sum accordingly to this function and calculating the h1, h2 and the output. While training, we will just make use of all these derivative functions we have calculated here and update our weights and biases. So let's look at learning rate. I am just keeping it 0.1, a constant learning rate. Epochs is the number of times you run through the loop and train your neural network. So I have kept it 1000. You can just keep it less or more depending on your training or the amount of data. I just kept it 1000 for the demo purpose. So for epoch this is just, I'm just looping through these epochs, the number of times this loop will run, and for all my input as well as the true value which is passed in the param, I'm just calculating the h1, h2 and o1. So here I'm just doing the weighted sum for h1, then passing it to the sigmoid function to calculate h1, same for h2. Then I'm using h1 and h2 to calculate the weighted sum for o1, passing it to the sigmoid function. Hence this is our y prediction. Now we know our dl by dy pred. We have already calculated these values, right? So our dl by dy pred is minus 2 into 1 minus y pred. We have our y pred, so we can easily calculate our dl by dy pred. Here let's understand this. This 1 is actually the y true, which is the true value for our data, which is 1, right? So here, as our data set was 1, we just put that as a 1 here, but it is actually y true. So here our y true is coming from here, from this input, right? So the formula has changed to minus 1 into y true minus y pred. Now for the neuron O1. Now O1 is depending on W5, W6 and B3, right? So we are calculating dy pred by W5. So to before updating the weights and biases, we need to calculate all these values, where is that, all these values dl by dy plot. So this in terms is, yeah, so to calculate dl by dw1, by what rate the input should change, right? We have to calculate all these three terms for each weight and each bias, right? Here in this sheet I have just shown the calculation for w1. Same thing we have to do for w2, w3, w4, b1, b2 and b3 before changing all of them. So this calculation was only for w1. So we are doing calculations for each of the weight and bias here, and similarly we are using the same formulas. So here, as we are calculating dl by dw2, we will just calculate dl by dw2, dl by dw3, dl by dw4 and so on. So that is what I am doing here. So w5 and w6 are simple h1 into derived sigmoid of sum o1. Sum o1 is this, right? So derived sigmoid is a function which calculates this thing f dash. So if you go to derived sigmoid, which I think I have written helpers, yeah, so this is same thing, fx into 1 minus fx. We calculated it here, right? So as we know, a dl by dw5 will be turned out to be, let me go back to my neural network training again, will be into h1 into a derived sigmoid of sum o1, right? Because our vibrate is directly depending on w5 w6, so we don't need to go one more step back, right? So this is simple, h1 into derived sigmoid of sum o1. Similarly w6 is equal to h2 into derived sigmoid of sum o2, because here if you will look into this, sum o1 is this, right? If you will take the derivative of it, which for w5 it will give you h1, for w6 it will give you h2, and this all thing is passed to the activation function, right? So we have to calculate the derivative of the sigmoid as well, right? Which I have extracted out as a common function. Same thing that we did here. This term. Oh, let me put it back. This term, we are just doing it in the code now. So we calculated our w5, w6, and b3. Here, if you will look into this formula, b3 is does not have a constant, right? So that is why it's simple derivative sigmoid of sum o1. I hope this thing is clear. If not, please watch it again, because this is crucial part of training a neural network. Similarly, we calculate our delta vibrate by delta h1 and h2, which will turn out to be w5 into derivative sigmoid of sum o1 and w6 of derivative sigmoid of sum o1, which is coming again from here. Earlier, here we are calculating based on w5, hence keeping the h1 constant. Now we are calculating the same function based on h1, hence keeping the w5 constant, which turns out this different results. Now we use these two values in our further calculations for w1 and w2 and w3 and w4, which we are doing here. So delta h1 by delta w1 is x0 into derivative sigmoid of h1. Similarly, s1 into derivative sigmoid of h1. For w3 and w4 are depending on h2, right? So x0 into derivative sigmoid of h2 and derivative sigmoid of x1 into derivative sigmoid of h2. Similarly, delta h by delta b1 is derivative sigmoid of h1, and delta h2 by delta b2 is derivative sigmoid of h2, sum of h2. So if you will take the formula of sum of h2 and try to find the partial derivatives based on delta w1, delta w3, w4 and delta v1, you will find the same result that I am calculating here. After doing all the calculations, we know we have to do this operation, where we update our weights and biases based on our learning rate and the loss derivative based on an input. So we know for w1, delta L by w1 means these three inputs multiplied together, right? Delta L by delta vibrate by delta h1, delta h1 by delta w1, right? Which we have calculated independently here. All these things are here. Now we will just multiply these three with our learning rate and subtracted by our weight 1. Similarly, we do for weight 2, bias 1, weight 3, weight 4 and bias 2. Now as you can see, in weight 4, weight 6 and bias 3, weight 5, weight 6 and bias 3, we don't have three terms. Here we have three terms, right? delta L by delta y pred by delta S2, S2 by delta W3. But here we have only two terms. That is because while calculating W5 and W6, our loss is depending on ypred, so it gives us delta L by delta ypred, and ypred is directly depending on W5, so which gives us this term. But for W3 and W4, we have to go one more step back, right? Because this depends on this output prediction, it depends on hidden layer, then hidden layer depends on W1. But in case of W5, output directly depends on W5. That is why the number of terms that are written here to calculate the loss is less. Okay, so after adjusting our weights and biases according to our loss, according to the derivative of loss, we just run our neural network again on the same input. So as this is a loop, right, 1000 times, so 1000 times the same operation will happen. So I'm just printing every 10 after running this loop 10 times, I'm just printing the result of all my y2s and y prediction. So after training it, I'm just printing the result. Let's see how it will look like. Let me check if the values are correct, and let me try to run this neural network training. Let's go to the terminal and just clean this up, and let me try to run this neural network .py, neural network training.py. So this was pretty fast because our data is less, our neurons are small. So as you can see, initially the loss was 0.28. Then the weights and biases got updated and the loss started decreasing. So as this is getting printed after every 10 epochs, you can see the loss is initially was more, and that started decreasing, and it became very less after 1000 epochs, right? So now we have these two predictions going on. So after we train our neural networks, after all the 1000 epochs, I'm just trying to predict on some random data. So this is my random data. These two persons were not a part of our training data. So this we call our test data. Now when I'm passing these two in my neural network, in my feed forward neural network, just to get the prediction of that person. So this will only do this calculation, this feed forward function, this small thing. It's not going into the train function, it's just going into the feed forward function. So it will just give me the prediction of the neural network, and it will not change weights or biases. I'm just taking out the prediction of my neural network, output of it. So as you can see, for Emily, we are getting a value of 0.952, and for this Frank, we are getting a value of 0.038. So as we know, in our training data, we represented the gender by integers, right? 1 and 0. So this is very much correct, right? This is very close to 1 and this is very close to 0. So if our data set is large and we keep on training our neural network with more epochs and all those things, this will get even more closer. So this is how we train our neural network, and this is how neural network learns and performs for a data set. I hope this video was good enough for you guys. If you enjoyed it, please give us a thumbs up, and we will see you in my next video.